I'm going to discuss a little bit about this relative error criterion for solving some ADMM subproblems. So this is a joint works. Probably it's going to be two parts. It's going to depend about the time. But so part of this work is collaboration with Max and Vando from Federal University of Goiás. And the second part, there's some collaboration with Renato Monteiro and Wei Kong from Georgia Tech. So I'm going to try to discuss a little bit two parts of the talk. So the first one is going to be about convex problems, and the second part is going to be about non-convex problem. But I'll give more emphasis on the first part. Okay. So we are interested in the ADMM method. So the problems that we are considering is this problem 1. Everyone have seen this. I'm just putting the notations. So F and G are closed convex functions. A and B are linear operators, matrices. So I'm just recalling that we have this Lagrangian system for the problem. So both problems are equivalent. We can solve the Lagrangian systems instead of the problem 1. Okay, so just reviewing the ADMM and to fix some notations. So we solve the first problem, and then we take the solutions and use to solve the second problem, and then we couple everything together in the Lagrangian update. So this is just the augmented Lagrangian. So the penalty parameter I'm denoting by rho. So what we have in this ADMM setting is that if you just do the first order optimality conditions, you come up with these inclusions and equation. Okay, so this is just the first order optimality condition for these ADMM subproblems. And then we have this lambda k tilde. So it's given by this expression. So what we are aiming to do is to see this ADMM subproblem as a point to set mapping, and then we want to see as finding a zero of this point to set mapping. So this is why I'm looking at this way. So we can see that there are some proximal terms that are appearing here. So of course, it may be kind of degenerate proximal terms, because I'm not saying that this B star B is an invertible operator. So anyway, so Michael already reviewed the Hpe method, but I won't take so long here. I may just give a reminder. So the idea of Hpe is to relax the proximal point method, as Michael already discussed. So the Hpe method has these expressions like here. So you have relaxed inclusion, and you have this relaxed inequality. So it's just to review. So as Michael said, so this Hpe method can be used to analyze many other methods, or maybe not the exactly form of this Hpe method, but maybe some variant of this method, but basically the same idea. So especially ADMM can be put in this setting, okay? And this was done by Monteiro and Zweiter in 2010, and they used this setting to analyze the iteration complex of ADMM. The iteration complex is like this remark 2. If you want to control the residuals, which is this epsilon k and vk, which are the residuals of this inclusion, and then the number of iterations is like this. So what is happening is in the epsilon residual, you get 1 over the tolerance, and in the case of v, you need to put the square here, so it's a little bit worse, unless you go to the ergodic sense. So if you go to ergodic sense, then you don't need to put the square. So in the pointwise case, is 1 over tolerance to square. And in the ergodic case, it's just 1 over the tolerance. Okay? So this is a very general scheme, and Monteiro and Zweiter analyzed this scheme, the iteration complex of this scheme. So it was first proposed by Zweiter and Solodov in '99, and they analyzed the asymptotic convergence of this scheme and many other methods. So what I'm trying to do is, for example, as I showed here, so we can see the ADMM as some inclusions and equality. So what I'm trying to do is try to solve this inclusion using the Hpe method. So this is the idea that I'm trying to discuss. So if you just try to see how is the method in this setting, so you come up with these 9 equations, inclusions and inequalities. So you need to find the next tilde and V such that the V is in this inclusion. So if V is 0 is exactly the first inclusion of ADMM. But in this case, it's a relaxed inclusion. So this X tilde needs to be controlled. So it's controlled like this, and it's exactly the Hpe method applied to this first inclusion. So there are some particularities because of this lambda tilde, how it's computed, but more or less it's exactly the same idea. Okay. So what we are doing, we are just analyzing the Hpe to solve the first subproblem of ADMM. And of course, we have a second subproblem, and the third there's nothing to do because it's just an equality, so there's nothing to do here. So we have the first subproblem and the second subproblem. So there are some issues I'm going to talk about it, but at first I'm just going to say that, for example, Jonathan and Bert Sekas analyzed this, how to solve the first subproblem of ADMM by using some absolute error, okay, some summable absolute error criterion. So this was done in '92. And then recently Jonathan and I think is one of his students, but I'm not sure, Jonathan Exton and Yao, so analyzed the ADMM based on some relative error criteria, okay? And I don't know, maybe close to this, almost the same time, I don't know. So this Shi, Liao, and Yang also had a similar idea for solving this first subproblem of ADMM. In fact, I think this is coming from because Jonathan and Paulo Silva, they analyzed a similar error criteria for the augmented Lagrangian. So I think this is like an extension to the ADMM. So and probably these guys also saw this method and tried to do similar things, and almost at the same time they got this. Okay, so there are some relations between this error criterion and these ones. Okay, should there are some mysterious here? Maybe Jonathan knows why. I don't know yet, because it's of this modulum. If you don't have this modulus, and the sigma 1 here, I should put sigma 2 because of that one, but if sigma 1 here is 0, okay. Now if sigma 1 is 1, and if you just do some calculations here, you can cancel this first term. And then what you have is almost this, but you don't have the modulo, okay? And then we just try to see how does this method works computationally, and it doesn't work. So it seems that you really need this modulo. If you take out, the method doesn't work properly. So there is some similarity, but what we do is, in our case, since we are looking at in the sense of Hpe method, we are not allowed to put this sigma equals to 1. In Hpe, you can do that, but this is the extreme case, and usually you have some problems. The idea is that somehow you would like to have some contraction property, and in this case, this sigma 1 needs to be less than 1. So as I'm saying, there are some similarity, but they're not exactly the same. But just to mention in the computational, in the numerical experiments, although they are preliminary numerical experiments, we did quite a lot of tests in this sense, and we could see that if you put sigma equals to 1, close to 1, not 1, close to 1, then this birth method has the same behavior. It's like exactly the same number of iterations, exactly the same behavior, but sigma is close to 1. If it's 1, then the method doesn't work properly, and it's different from this one because of this modulus. Okay, so there are some relations. It's not so clear, but there are some relations. So how is the algorithm in this sense? Okay, so we have this error tolerance criteria here, relative criteria. I'm sorry, parameters. I'm sorry. So we have this relaxation parameter. So it's going to depend on the sigma 1. So if it's 0, so you see, if it's 0, then you have 1 plus the square root of 5 over 2, which is the golden number that we know that the relaxation parameter needs to go up to this number. So the method is like this. So the first subproblem you solve like I said, for example, using the Hpe method, the same idea of Hpe method, and then you just update this lambda tilde. So the second subproblem, of course, the natural question is, why do not use also the Hpe in the second subproblem? So there are some issues I'm going to talk about. So what we did here to at least to alleviate a little bit this problem, so we put a proximal term here, and as everyone here knows, so we can use this appropriately in such a way that we can alleviate this problem. And also, at least in the numerical experiments, the second problem is solved exactly. So at least from this point of view, there's no issue. The second problem can be solved exactly. But from a theoretical point of view, what we would like to do is to put a similar criterion here. But we can do that. But what happened here? I'm interested in this relaxation parameter. So in the Eckstein's paper, he didn't consider the relaxation parameter. He considered this inexact version, but the relaxation parameter is equal to 1, so it's the pure ADMM. So we are kind of interested in this relaxation ADMM. So in this sense, if theta is equal to 1, then we can put also this Hpe scheme here. But since we are interested in theta larger than 1, there are some issues, and the issue is related to because when you put this parameter, the calculations are quite more involving, and you need to use some angle property. So of course that I'm taking for those who have already done the calculation around these things, so they will recall and recognize that there are some angle properties which is related. For example, let's say when you solve here, you can say that 0 belongs to subdifferential of G minus B star lambda k, where lambda k is like this. So we use this expression to have an angle property, and this angle property is essential to analyze the relaxation ADMM. So this is the issue. There is an issue here, and the only thing right now that we can do to avoid this issue is to put this proximal term. But in our numerical experiments, the second problem is solved exactly. So that's why there's no many problem. We just focus on the first subproblem. And similar things also happen in the paper of Jonathan Eckstein. So if you just analyze the optimality condition for this method, so you come with this inclusion. Then what is happening here, as you can see, it's like a prox inclusion. Okay, so you have here the proximal terms. And this also can be seen as a residual. So the idea, what we do is we want to measure this residual in some sense. So, and we want to say, okay, how many iterations do I need to do in order to have this residual small enough, given by some tolerance? So this can be rewritten in a different way, which is like this. So you have this inclusion, and M is this matrix, T is this operator. So what we have seen is that, so the subproblem, we are using the Hpe method, but what is happening is the outer procedure is also an Hpe type method. It's a modified Hpe method, especially because when you do some calculations, you also see this inequality. So it's like in the inner subproblems, you are using Hpe method. But in the outer subproblems, you also have an Hpe type method. But there are some modifications, you see. And the expressions are quite involving. It doesn't make sense to go into details in these expressions. But what's matter is this 21. So this is close to the Hpe inequality. Let me just review here. This one, for example. It's very close to this one, but we don't have this epsilon, and that eta k appears in both sides. So the ADMM, it's like you need to do some modifications in order to analyze in the setting of the Hpe method, okay? So there is some, but these modifications can be handled, so that's not a problem. So the modified Hpe framework or method is like this. So it's exactly the same expression that I got in the ADMM procedure that I've just showed. So you have the inclusion, and here you have an operator. At first, I'm not saying that this operator is invertible, okay? So there are some issues. It could be degenerated case. And you have the inequality that you need to control somehow, the errors, as Michael said. But there are two modifications. One is this parameter eta k, and the other one is this linear operator M, which is also appear here. So there are some, you could analyze the degenerate case. Of course, there's maybe some issue, but you can analyze this. So in this Hpe framework, in this modified Hpe framework, you have the same complex results of the usual Hpe framework, okay? But things are just modified to take into account these operators, but still are the same results. So this is the ergodic case. So you just take some averages, and what is happening here is that you see that there is some improvement, as Michael already discussed it. So if it's a pointwise case, if you don't take any average, so it's 1 over square root of k. K is the iterated count. And if you go to the average case, the ergodic case, so you don't have square root of k. So this one, in terms of iteration complexity, is better, but the problem is that you are relaxing you are considering a larger set instead of the operator t, because here is the operator t. There is no enlargement here, okay? But it's still, this modified Hpe has the same properties as the usual Hpe. So in this sense, we can just put the ADMM in this context, and of course the expressions are a little bit more complex, but it's still the same idea, and you just apply this Hpe framework, and we have the iteration complexity. The averages are a little bit more complicated, but you can do. So yeah, that's it. For example, what is happening in the inner scheme to solve the first ADMM subproblems, we apply the Hpe method, and the outer scheme, which is an ADMM type method, can also be seen as an Hpe method, but it's a modified Hpe method, but it has the same iteration complex properties. So this is what all of these results are saying. So in the numerical experiments, I won't go into detail, but just to give an idea. So we followed similar approach as the papers of Professor Jonathan Yao, which is, as Michael already mentioned, this parameter, it's saying that we relax as much as possible the relative parameter. Here also, if we put close to 1, then the method is very close to the one that Eckstein proposed, which is this one. So we compare both methods in quite a number of numerical experiments and tests, and both methods behave exactly the same. The number of outer and inner iterations are exactly the same if this parameter is close to 1, and we follow similar formula of their papers to make things fair. So here the outer tolerance is not I don't know, it's not so stringent, but it can give us an idea. And also in their paper they mentioned that there are some issues when you are close to the solution. Sometimes this criterion is not so easy to pass. This one is going to pass easier. And the same issues also happen with our approach. So we just mix things. If this V is very small, we just stop the inner and just continue. But most of the time, the method is going to proceed using the scheme proposed. So we just testing some lasso problems. We solve the subproblem using conjugate gradient method and using these relative error criterions. So the first and second column here, as I told, for example, this one is the Eckstein method. This one is our approach. And as you see, the outer and the inner are exactly the same, and it's not just here in all of the numerical experiments this happen. If it's not the same, it's a very small difference, nothing that should worry about. So both methods behave the same if you have the relaxation parameter equals to 1, okay? So if you put the relaxation parameter equals to 1, both methods have the same behavior, numerical behavior. So, and then we just test what happens if you just move the relaxation parameter. So as you can see, if theta is close to, is 1.6, which is close to the golden radio, then the method it's a little bit better. But still, these are just preliminary numerical experiments. I know that the numbers are not so good that we would like, but still, we didn't do any tune-up, so we just did like exactly as Jonas' suggestion in his paper, and just did that, so we didn't tune up anything. So these are the fair numbers, okay? Okay. So we also consider some problems that come from applications, and we also follow his paper. So as I say, these numerical experiments are very close to what he did in his paper. And for example, in these numerical experiments also, the outer and the inner are very close. The methods behave exactly the same if the theta is equal to 1. So if you have relaxation parameter, 1.6, so the numbers are a little bit better, okay? The inner, for example, in this case, you see the inner are quite considerably different. This one also. So the numbers are, the number of iterations, even the outer and the inner are still better, not as much as we would like to, but it's okay. So I'm just talking a little bit about the second part of the talk, which is discussed a little bit of ADMM in the non-convex case, okay? So recently, Wotawin and also many of you here have analyzed this method in the non-convex setting. So we also start to do some things in this setting, and so the assumptions are similar to the ones that people have already mentioned here yesterday. So I think there's no many things to go into. This A1, I think Wotawin consider this one is close to say that the matrix B is row rank, full row rank. Okay, so the second function here needs to be differentiable, as both already discussed this issue. So we consider the case in which instead of saying that only the gradient is Lipschitz continuous, you have an upper curvature and a lower curvature, and we are interested in the case in which the lower curvature is smaller than the upper curvature. So I'm going to discuss a little bit about this. So the hypotheses are similar. I think there's nothing to say about this. So the proximal ADMM is the one that we analyze in this non-convex setting. Okay, so we did the relaxation, and what we got here is that all of the previous papers, the relaxation parameter can be just up to the golden ratio number. Okay, so square root of 5 plus 1 over 2. So all of the previous papers, and what we realized is that since we are changing the penalty parameter, let's say here, since we are changing the penalty parameter, because in the non-convex, in the convex case, the penalty parameter doesn't need to be large. It doesn't matter, at least from a theoretical point of view, it doesn't matter. But in the non-convex case, all of the papers requires that this parameter needs to be sufficiently large. Okay. So since we are allowing to move this parameter, we realize that we can also, by doing this, we can enlarge the interval where you consider the relaxation parameter. So in this non-convex setting, we can go up to 2 by moving the penalty parameter. Of course, this will also work for the convex case, but in the convex case, it's not interesting to move this parameter, even in the non-convex case. But the non-convex case, there's nothing to do much about it. It's required that you need to do a large penalty parameter. So since it's required that, so we are able to do the relaxation up to 2. Okay, and what we get is the iteration complex that you solve in exactly the first inclusion, and you control the feasibility, you control this error, and we control the second, because now it's not in inclusion anymore, it's equality because G is differentiable, so you also control this error. And the number of iterations is bounded by 1 over the tolerance to the square. Okay? So the iteration complex is the same as the ones that had obtained before. So the main issue here is that we got close to 2 instead of square root of 5 plus 1 over 2. Okay? So, but what we realized here is that the second problem, it has an issue because we are moving this penalty parameter to be large. So if you just check what is happening in this upper and lower curvature, the upper curvature is usually it should be very large, okay? At least from a theoretical point of view, it needs to be very large. And then we are in this setting that we have this problem, minimizing a function, which the lower curvature is usually very small compared to the upper curvature because of this, okay? Then you just start to see how can we solve this problem. So we can put this in a different way. You have a composite function, which is a smooth, possibly non-convex, and a non-smooth but convex. Then we want to solve the problem of minimize this function where the upper curvature, usually the upper curvature here is denoted by big M. So this is usually larger than the little m. So you just come up with a method which is like this. For example, you regularize the function by a proximal term. And then what you do, you just apply Nesterov method to this proximal term, but in such a way that you are controlling the iterations of the Nesterov method in terms of a relative error criterion, which is closely related to the Hpe type method. Okay? Then you apply this scheme until this inequality holds. This rho bar is the tolerance. So if it holds, then you go to the next step. If not, you keep doing this until it holds, and we show that it's going to hold. And it's not going to take so long to solve this this scheme here. And then what happens? Once you solve this scheme, you just go back to Nesterov method and just continue. You don't start a new Nesterov method, just continue. And if you do that, you can show that you are going to control the epsilon parameter. Then once you have this scheme done, just go to a refinement procedure in order to improve the solutions that you have. And the refinement procedure basically is just to solve a subproblem which is which is the same in the same sense in the Nesterov method. Then you just solve this one subproblem, and then you have your approximate solution. So we just count all of these iterations, and the number of out iterations is given by this, where here you have the lower curvature, and the total number of iterations is given by this plus a log term, and you have an approximate solution in this sense. So the epsilon is here in the non-smooth part, the V is the residual, and the epsilon also can be said as a residual, and we measure V and epsilon, and the number of iterations required goes up to a tolerance is given by this. So the square root of big M and little m. So this is what we are interested in, because if this big M is very large compared to little m, so this scheme it seems to be better than ones that have been proposed in the literature for solving this problem. So up to now, I'm not saying that we can use this scheme to solve the ADMM subproblem. I'm not arguing that, okay? I'm just saying the second ADMM subproblem has this particularity that the upper curvature is large compared to the lower curvature, and then we came up with this idea, and we have this problem. So this was done by me, Monteiro, and one of his PhD students from Georgia Tech. Okay, so these are the reference. So you can find. Okay, thank you very much.